We are Wisconsin Robotics, and we are proud to present our 2022 Rover Daybreak. Our focus has been on increasing the reliability and robustness of our design. This included creating stronger wheels, redesigning our arm, and developing new science tests. We also made improvements to our chassis box and code quality to fully improve our Rover for the University Rover Challenge.
The drive system utilizes a 6-wheel design that has a rocker bogie mechanism with a vertical differential bar that allows the Rover to navigate through rough terrain with relative ease. The design is made to withstand heavy impacts without needing heavy springs and dampers. The Rover's 6 wheels are made from a Kevlar epoxy mixture, which is a stiff but also malleable enough to withstand large impact forces that will occur when driving the Rover at full speed. On the top of each wheel are grousers that are made of rubber and will provide traction when driving across rough terrain, such as sand and rocks. These wheels are attached to the motors via aluminum spokes that are attached to a wheel hub. Each wheel is powered by a bag motor made by Vex, attached to a 7-to-1 Versa planetary gearbox that will provide the bot with a high torque ratio while still allowing the bot to reach high speeds.
Daybreak has a 6 degree of freedom, kinematically redundant arm.
The arm is designed to maximize joint efficiency in lifting while minimizing weight. The arm can reach the full 1.5 meter height range. Encoders will be integrated at each of the joints to allow the use of inverse kinematic control, thus enhancing overall usability of the arm. The arm features increased joint stability to reduce backlash and facilitate inverse kinematic control. Each current draw in the arm will be limited to reduce the chance of motor burnout during IK operation. The end effector uses a high torque and zero backdrive system. The claws of the end effector can grasp more than the full 5 centimeters. The tips of the claws are flexible, allowing them to conform to the object they grab. The end effector will be able to manipulate the full range of objects that it may encounter in the competition.
The electrical system of Daybreak is improved from our previous Rover designs.
For starters, we have upgraded the cameras in order to improve our robot's vision. This will help us when looking through the cameras and with lag reduction. Next, we have upgraded our Reaper board from last year with a new custom-ordered PCB in order to optimize the distribution of power across Daybreak. Another important change that we have made is the modification of the chassis box in order to support cooling and prevent the inside components from overheating. For the autonomous portion, we have upgraded our LiDAR to improve performance with less human input. A new addition this year is that we have put a distance sensor on the front of the Rover to help with cliff avoidance. We believe that all these changes will improve our Rover overall.
The focus for software this year was improving the robustness and functionality of Daybreak's code. Using a 4-layer abstraction model, we're able to compartmentalize program responsibility and develop highly modular, reusable code. This software is modeled in a building block approach where simple programs are written in C++ or Python and linked together using the ROS Noetic framework.
We have developed a robust driving and control system for the ERDM challenges, focusing on quick response times and safe operation. We also adapted our serial communication software to provide extra motor functionality, such as encoder and current feedback, for safer and more intelligent motion control. We are currently developing intuitive IK-based arm controls for better manipulation, tuning our long and short-range navigation algorithms and sensors for the autonomous driving challenge, and creating a hardware layer program for our new drive motors to take advantage of their improvements while minimizing the impact on other software projects.
Daybreak features a balanced array of tests for detecting life, assessing habitability, and analyzing rock samples.
Our custom scoop mounted to a crossbar collects soil, depositing each sample into a funnel system that distributes it evenly between our chemical tests. On the turntable, the Rover tests for proteins and ammonia as prominent biosignatures, and nitrogen, phosphorus, potassium, and pH as indicators of habitability. For geologic analysis, a 300 times microscopic imager and moisture sensor are lowered into the ground by spring-load linear actuator, revealing signs of fossilization and the presence of water. We've also been prototyping a Raman spectrometer to search for organic molecules and a swappable scoop system to reduce cross-contamination.
The team leverages several testing platforms and environments to prepare Daybreak and our operators for completing tasks in the competition. For manipulation preparedness, the team uses a test box that contains many of the equipment servicing and ERDM challenges. Side panels of the box hold tasks such as switches, USB port, and the keyboard to practice fine manipulation. The overall box weighs 5 kilograms and has a rope to test arm and grip strength. The software team uses a miniaturized robot that contains identical hardware to the Rover for writing and testing software. This platform allows testing of autonomous, teleoperated, and drive system code without needing the entire Rover to be operational. The team will be using the campus for full system testing, focusing on communications, the drive system, and teleoperation practice. With our system design and our preparedness for the competition, Daybreak and Wisconsin Robotics will be more than ready to tackle the 2022 University Rover Challenge. Thank you to our sponsors.